Okay, this chapter is Graphs and Transformations, Pure Year 1, Chapter 4. And this actually kind of comes up in a lot of other future chapters, so be aware it's not going to always come up in this form in the exams. It's probably going to be combined with some other topics. So we're going to start off with some cubic and quartic graphs. And when we sketch these kinds of graphs, we need to think about mostly these three kinds of things that we've got here. So when we think about the shapes of different graphs, we've got the positives and the negatives. Well, I'm going to start with some stuff with quadratics as well. We know that a positive quadratic is this kind of shape. And for a positive cubic, it's usually this kind of shape, so going down from the bottom left to the top right, or it may have some more kind of extreme wiggle in it like that. And then for a quartic is either going to look like a quadratic shape, or if it does have some wiggles in it, it has like four kind of lines to the wiggles. So it'd be starting from the top, so it'd be like 1, 2, 3, 4. And quartic is obviously something that is a power of 4 that we've got here, but it doesn't always have to have these bumps or wiggles in it. They can look slightly different to this. Now, negative is going to be like these ones, but flipped over. So I'll do them in a different color. So a quadratic, we know, is that kind of shape. A cubic will start from the top left and then kind of come down to the bottom right, or it could have that wiggle in it. And again, for a quartic, the branches will be down in the negative section. So a quartic could be like this kind of shape with both branches finishing in the negative part. And I explain in my videos why they are this shape. But for this one, as it's just a bit of revision, we're just going to kind of run straight with it. So for roots, when you have a root, these black lines that we've got here are representing the axes. We know that when you have a root, it just is going to represent it literally crossing a particular part of the axis. If we have something which is a repeated root, it means it's going to come down to the axis, it is just going to skim it, and then it is going to go back up again. So that's what a repeated root would look like. And if there is no real root, it just means it's not going to be touching the axis at that particular point. Little side note, if we had a repeated root where there was, say, a triple repeated root, so it was something like, I don't know, an x cubed, we would have the line, and for the curve, it would kind of look like it was about to do a repeated root, but instead of going down, it would kind of like pass, oh, it's gone a bit funny there, it would like pass through it like this. So if you have a triple repeated root, it kind of looks as though it's about to do a repeated root, but it does still pass through, but you can see how it looks different to this standard root that we've got there, but it's quite rare for that to be asked. I'll leave it on, but you don't need that as sort of the main bit. And then I've put y-intercept here because if we do know the y-intercept, we want to indicate what the y-intercept is. So the question says, sketch the following curves on the provided axes. We've got this one, and this one here. And you want to do probably a lot of practice of these so you really know what you're doing. So for this one, we have a cubic because we've got an x, an x, and an x. This is a positive, and a negative. So it is going to be a negative cubic, which means it's going to be this kind of shape in general, starting at the top left, going to the bottom right. And the roots that we've got, there is a 0 root for this one, so I'm just going to mark that in. Then we have, for the next part, we have a 3 root, because I'm trying to make the bracket 0, so there's going to be a root somewhere on the positive side. And then there's a -1 root, so somewhere on the negative side. And the reason I'm doing it with arrows is because if I put the crosses in here and here, and then I try and draw it, I always find I miss them. So instead what I'm doing is I will roughly aim where to put them, and then afterwards I'll put the crosses in. So it's a negative, which means it's going to be starting from the top, and it's going to be crossing somewhere in this negative part. It is then going to cross at the 0 part, and then it's going to be crossing somewhere over there in the positive part. So I'm going to get rid of those little arrows that I did, and I can now just indicate that the point where it crosses here was a -1. Obviously that's a 0, it doesn't even really need a label, and this point here is a 3 that we've got. This doesn't need to do anything for the y-axis because we know it's going through this point, and it's obviously 0 that we have there. Okay, so the next one that we've got is this. Now decide if it's a cubic or a quartic. I think it's a quartic because we have 1, 2, and then 2 more x's coming from here. So it's going to be a quartic. And it looks like it might be a negative, but actually that's going to be squared. So it's going to become a positive, positive, positive. So it's a positive quartic, which means it's that kind of shape with the branches both going in the top section. Now we have a repeated root that's going to be over here at 2. So if the repeated root is over here, I kind of do the repeated root with like more of an asterisk rather than a cross. We've got another root that's at 3 somewhere over here, and another root that is at -3. And you don't have to worry too much about how accurately they are because it's just a sketch, okay? So I will start from a top part. It's going to come here. It's going to pass through this point. And then this one is a repeated root. So because it's a repeated root, that means it's just going to skim that point and come back down again, which then means it's going to go back up through this place. So I have that as my -3, my 2, and my 3. So I've done the shape and I've done the roots. I just need to check the y-intercept here. Now to check the y-intercept, we just want to make x equals 0. So if we just subbed 0, 0, and 0, I would have 2 squared times minus 3 times 3. So that's 2 squared, which is 4, times minus 3 is minus 12, times 3 is minus 36. So again, it doesn't need to be properly drawn to scale. That is a perfectly acceptable sketch for that quartic. And then the last one that we've got here, we have a cubic, because I have a quadratic and I have a linear one. And if you check this part, and you can do this yourself, I won't waste our time. If you check the discriminant of this, this is a negative discriminant, which means it has no solutions. So there's only going to be one root for this cubic, which is going to be at 2. Okay, so I'll put that as root 2. So I'm going to say this is passing through one point. It's obviously a positive shape like this, because we have no negatives for the x part. And I'll check the y-intercept. The y-intercept is when x is 0. So when x is 0, we have a minus 2 and a 4, which is a negative 8. So that means it's going to be crossing somewhere on this negative part of the axis. So it might look like this. It could look like it comes up here, and then there's like a wiggle, and it comes up like this. Or it could look something where it just goes through that line and it has a very gentle wiggle in it like that. It's really difficult to say until we've learned some further parts of this, what this cubic might actually look like. So I'm just going to leave it in this particular form. I'm going to say it's going to come up from the minus 8. It's going to go here. And I'm going to represent a little wiggle in this. I don't know what it's actually going to look like unless I graph it on some software. But I'm not really bothered about it in this particular chapter. Later on, we work out how to find out, is there a minimum point somewhere later on? Or is it one that just kind of goes like sort of straight off into the distance, which is still a type of cubic that we have there. Okay, we now want to talk about reciprocal graphs that we've got here. And we've got these 4 different kinds. And a little exam tip is, if they do ask for, when you're asked to sketch something, it would typically ask where a graph intersects with the axes, as well as any equations of the asymptotes. And we know what an asymptote is, hopefully, but I'll use this opportunity to explain it too. So a reciprocal graph, something like here, I said that y equals k over x, where k is greater than 0. I don't know, this could be something like y is equal to 2 over x. I'll just very quickly draw in some very simple axes that we've got like this. And that is going to be where we have it kind of this sort of curved shape here and this curved shape here. So we have it in these 2 quadrants of the graph like this. And in terms of asymptotes, this is an asymptote, which means the graph approaches it but never touches it. And this is also an asymptote. So the x and y axes are both the asymptotes for this. Now the difference in this second graph is that we've said that k is less than 0. So this could be something like, I don't know, y is equal to minus 3 over x. Now minus 3 over x, if it was 3 over x, it would be sort of further away from this one. So the bigger the numerator, the further away that it gets from the axes. If it's a small numerator, it would get closer towards the axis as well. So for this one, because it's a negative, it's just going to be in the other 2 quadrants that we've got. So it's going to be in this section and this section here. And again, we have the asymptotes as the x-axis and the y-axis, which we could either say is y equals 0 and x equals 0. I suppose if I was being a little bit fancier, I should say this is x and this is y, but I don't think they're too fussy about this. Now the difference with this one, we have it as an over x squared. Again, the numerator is positive, so this could just be something like y is equal to 1 over x squared. So because the x part is being squared here, we're never going to get a negative x, because when you square something, you always have a positive. So the difference for this one is that we are going to have the branches both up in these 2 quadrants. And actually, they kind of hug the curve more tightly than this one. Because x is being squared, it kind of hugs the axes more closely. And again, we do have the same asymptotes of the y-axis and the x-axis. And I'm mentioning this because if we do any transformations with these, we may need to move the asymptotes as well. And then our last one that we've got is for this kind of graph, where this time we've got that we have k as a negative. So it's going to be the same as the other one, but just flipped down to the bottom like this for our y and x. And of course, these are the asymptotes here and here. So what we're going to do for this one is it says sketch y equals 3 over x squared and y equals x squared x minus 2 on the same set of axes, and use your sketch to determine the number of solutions to this equation. Well, that's a bit of a strange bit. Let's actually start off with the sketch to begin with. So we're going to do the 3 over x squared. It's going to look like this kind of graph. And again, we don't know exactly what it's going to look like in terms of how close to the axes, but all we're really looking for here is just the general shape of it like this. Not too bad. And then the next one we're going to do is the x squared x minus 2. So it is a cubic, so it's going to be this kind of shape. And we've got a repeated root at the origin here, and we have another root that is a 2 like this. So putting that all together, and I'll do this in a purple color, we're going to have a repeated root at the origin, which means it's going to start down here, and there's going to be that skimming at that place, and then it's passing through 2, which means it's going to come up like this. So I'll label that as a 2. I don't need to worry about the y-intercept. I suppose if they wanted to know the asymptotes, I could say the x and y axis for this one, but that's more for if we have any transformations, we'd need to be more careful of that. So that's the sketch, and we're trying to say something about the number of solutions to this equation. Well, it's definitely related to this graph, so let's see if we can see how this thing is related to these equations that we've got. Now, my instinct is it's going to be about where these two graphs are crossing each other. So let's see if that actually makes sense by having a look at 3 over x squared being equal to x squared x minus 2. So if I were to expand the brackets on the right hand side, I would get x cubed minus 2x squared. And now you can very quickly see how it's related to this one. It's just multiplying the x squared up onto the right hand side so that we get 3 is equal to x to the 5 minus 2x4. So what we can say here is the solution to the equation is represented by the graphs. It is represented by the graphs. They only cross once, so there is only one solution. They cross only once, so only one solution. And that solution would be the x value here. So that x value is going to be somewhere close to 2 in terms of the x part being the solution to that equation. That's quite a strange thing that this equation obviously has the same solution as this one because we haven't fundamentally changed the equation. This was the two graphs being equal to each other. This was the equation that was being talked about in the question. Now we can look at graph transformations, and I split these into stuff to do with the y direction and stuff to do with the x direction. Y direction meaning going up and down, and x direction meaning left and right. Now the y direction kind of behaves how you would expect. The x direction stuff is the thing that does what you would not expect, or kind of like the reverse of what you think it might be. So in terms of this first one, we have f of x. If you have a function and you add a to it, it is going to transform the graph by shifting it a spaces up. And we would write that as a translation, and the translation is going a spaces up. So with a vector, remember from GCSE, the bottom number means how it moves. So we're going to say it's going a spaces up, how it moves upwards, that bottom number. Now, if we have the a in front of it, we can either call it a stretch or an enlargement. I'm going to say it's a stretch in the y direction. I'm just going to do an arrow to show what I mean by this, going up and down. And the scale factor is a factor of a. So it means it's going to be multiplying in the up and down direction by a scale factor of a. And then the last one is a reflection in the x-axis. And you're probably thinking, well, hang on, I thought we said it's in the y direction, but that's because a reflection can also be thought of, if this is the y-axis that we have here, it can be thought of as flipping over, that's not the y-axis, the x-axis. We can think of it as flipping over the x-axis, and it is still happening in the y direction that we've got there. And really, it's just a particular application of this one that the scale factor is a negative, and we know that negatives means it flips things around when you remember stuff from GCSE transformations. So for the x direction, they're going to be the same things, but with a slight twist. So for the x direction is going to be a translation, like we just said on the previous one. But the vector for that translation, you'd think it might be a 0 because it's in the x direction, but it's actually minus a. It's actually doing the opposite of what you think. So it looks like you're adding a spaces for it to move to the right, but it's actually going to move a spaces to the left. This one is a stretch, and it's still going to be happening in the x direction. And with arrows, I mean it's happening like this and this. But the scale factor this time is not a, it is 1 over a. So actually when you multiply something, let's say it was a 2 here, you're actually squeezing it in. You're not stretching it out, you're actually squeezing it in by a factor of a half. And we still can use the word stretch or enlargement, but when we have a scale factor that is less than 1, we know it means like a compression. And then this one kind of is just the opposite of this. It's going to be a reflection in the y-axis, meaning in the left and right direction. So this is a reflection in the y-axis. And what I mean by that, there's my y-axis. It is going to be reflected. Let's just quickly write this, y-axis. You can see it's going to flip over that line. So this is going up and down, left, left and right, left and right. So that's why I've kind of split them into these two groups. So we are going to, for these graphs that we have here, it says sketch the following transformations showing the coordinates of any maximum or minimum points and any known intersections with the axes. If we don't know the new intersection, we don't need to put it in. So here is my original graph, f of x, and I'm going to draw y equals 2f of x for this. So that means it's going to be stretched in the up and down direction by a scale factor of 2. So it's actually going to be more steep like this. This is not going to be my finest hour in terms of drawing. And instead of it going to 7 over 2, it's going to stretch all the way up to 7. It's still going to cross at 0 here because 0 times 2 is 0. That minimum point is going to come down lower. It's going to cross at the 4, and it is going to stretch up more like this. Now it's still crossing at the 4, the 2, and the minus 2. I just need to relabel this point, which this point here is going to be a 7 instead of a 7 over 2. And this minimum point is still at the x coordinate of 3, but it's stretched down to minus 4. Okay, the next one that we've got is a minus 7 over 2. It's outside of the brackets. All of these ones are outside of the brackets. These ones are all inside the brackets. So we're shifting down minus 7 over 2. We're going down 7 over 2, which means that it is going to cross at this point instead. So it's going to go like this, come down here like this, and it is going to, I'm never very good at drawing these as they come down because it is still going to want to be like this, isn't it? Tell you what, I'm going to do something very, very, very sneaky, which I can do because I'm on here. We'll make it look even neater. If I take the graph and I'm literally going to just drag it down so I know I get it looking how I want it to look, because I didn't want it to cross over, and as I was drawing it, it was crossing over. I knew it wasn't meant to cross over any of those places. So I don't know this intersection with the axis, so I'm not going to work it out, but I'm still going to see this is obviously 0, and this point has moved down. So it's moved down 7 over 2. So minus 2 minus 7 over 2. That is, I think, minus 11 over 2. Yeah, that's right. Okay, then we've got this one here, which is an f of x plus 2. So we know what that means. It's going to go 2 spaces to the left. So I'm going to do this a bit sneaky. No, I'm not. I'm actually going to draw it how I want to. So I was going to do that same thing of drawing it on good notes and then shifting it along. But this one that's at 4 is now going to be crossing at the 2. The 2 point is now going to be crossing at the origin, and the minus 2 point is going to be crossing at minus 4. So it's going to come down like this. It's not particularly well drawn to scale in the first place, but we get the idea of what I'm trying to show here, and it's coming down here. So that's a minus 4. That's obviously a 0, and that's still a 2. Now that minimum point that we've got here, it was 3 minus 2. It's now 1 minus 2 as it's moved 2 spaces to the left. And this point was previously at 0, 7 over 2. It's now at minus 2, 7 over 2. These diagrams can get a little bit messy. And then our last one that we've got is f of minus x. It's inside the bracket, so it's to do with the x direction. That means it's a reflection over the y-axis. So it's previously crossing at the 4, so it's going to be at minus 4. And then it crosses at 2 on the right-hand side, so it will cross at minus 2. And then it will cross at this one over here. So it's going to come down like this. Then it's going to come up. Very hard to draw these reflections, I find. So it's crossing at minus 4. Minus 2 is still labelled, and the 2 is still labelled. This is still the same point of 7 over 2. That should be at the same point. And it's just this other one over here. So this minimum point is a minus 3, minus 2. Very, very annoying drawing these. Hopefully they give you a nice big bit of paper to do this in the exam. So our last part here says that the point 7 minus 3 lies on the curve with equation y equals f of x Find the point to which P is mapped when the curve with the equation y equals f of x is transformed to the curve with these equations that we've got here. So if we had a coordinate x, y, I'm very quickly going to write what would happen with these, and then I'll write what the new coordinate would be. So this one just means 3 is being added onto the y coordinate. So it would be an x, and then the y coordinate is going to be 3. It's just moving 3 spaces up. So the new coordinate would be 7 and 0. This one, the y coordinate, is just being multiplied by minus 3. It's just the stretching in the y direction. So it would be an x and a minus 3y. So that means it was previously 7 minus 3. If I multiply minus 3 by minus 3, we get 9. Now, technically, these two are not in this part. They're more in year 2, but I think you can handle 2 transformations at once here. So the xy coordinate is going to change in 2 ways. The x coordinate is going to have 1 subtracted from it because of this part. The y coordinate is going to double, so we get 2y, which means that the 7 becomes a 6, and the minus 3 for the y coordinate becomes a minus 6. And then our last one that we've got here, the old x coordinate, we've now got a third x. That means it's going to triple the x coordinate, so it'll be a 3x. And this plus 3 at the end means we're going to add 3 on to y. So it was previously a 7, it's now a 21. It was previously a minus 3, so it is now a 0. So this would be the location of P, given all of those transformations that we've got here. So I hope you found this useful. This is the beginning of a series of this. If you do like this, it's very helpful for me and for the algorithm to just say, give it a thumbs up, say that you enjoyed this video, and I will keep making these so that hopefully we get them all made for all of A-level maths. Okay, thanks guys, good luck, and hopefully see you in another video soon.